Okay, in this section, we're going to look at the Laplace transform of a derivative of a function, and then also for the integral of a function. We start with just a few formulas. These are definitely, the first two are the ones we'll find that we'll use the most often, that just tell us how to find the Laplace transform of f prime and f double prime if we know the Laplace transform of f. And then we can extend that to any higher order derivative using the formula number 3. These aren't anything you need to memorize, but they'll be handy, so you want to be able to refer back to them. One way in which we can use these formulas is to help us find the Laplace transform of certain functions. So let's say our function is t times sine of omega t, and we want to find the Laplace transform of this function. Well, the first thing I'm going to do is take the first and second derivatives. So if we start with this function, note that f prime of t, we're going to use the product rule. So we're going to get sine omega t times 1 plus t times cosine omega t times omega. Let me just clean that up a little bit. So there's our first derivative. And from this, before we get the second derivative, we'll just note that from the given function, right, f of t is t times sine omega t. We can find f of 0, and that'll be 0 times sine of 0, which is 0. And we just found the first derivative, so f prime of 0. Let's see, when we plug in 0, our first term is sine of 0, which is 0. Plus, and then the second term has a factor of t, so that'll be a factor of 0. So the whole thing ends up being 0. So our first and second derivatives evaluated at 0 give us 0. I'm going to find the second derivative now. So derivative of sine omega t is omega cosine omega t. And then we got a product rule again here, so we'll do, let's see, so it'll be omega times cosine omega t plus omega t times negative sine omega t times omega. And cleaning this up a bit gives us, let's see, these first two terms here, that's 2 omega times cosine omega t. And then we have a minus omega squared t sine omega t. So there's our second derivative. Now that we've found the second derivative, I'm going to use this result in item 2 here. So note that the Laplace transform of f double prime, that's going to be the Laplace transform of this stuff, right? The Laplace transform of f double prime, I'm just going to put this function that we found for the second derivative. And the Laplace transform is linear, so I can split it up over this subtraction here, and I can also pull out the constant factors. And the constant factors, of course, that doesn't include the t, but it includes the omega, the 2 omega and the omega squared. So this is 2 omega Laplace of cosine omega t minus omega squared times the Laplace of t times sine omega t. And here's what's interesting and maybe hopefully useful to note at this point, and that is that we see our original function that we were interested in, right? Here's our f of t function up here at the start. That shows up again, right? So this function right here is equal to our f function. So I'm just going to make that substitution. And this is the Laplace of f double prime. Okay. So now we'll actually apply the Laplace transform to this first function in the first term. So that's this right here. We know the Laplace transform for cosine. That's in our table. So we have 2 omega times s divided by s squared plus omega squared minus omega squared times the Laplace transform of f. So this is the Laplace transform of f double prime. We've done this just by finding the derivative and then applying the transform and noticing that our original function f showed up again, and that one of the terms was a function for which we already know the Laplace transform, namely cosine of omega t. Now we're going to use that second formula. Now we're going to use that second formula that says that the Laplace transform of f double prime is equal to s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. Okay, so this is s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. Now back up at the top, we'd already computed or evaluated the function and its derivative at 0. We found that f of 0 is 0 and so is f prime. So this is 0, that's 0. And so now we have our equation that 2 omega s over s squared plus omega squared minus omega squared times the Laplace transform of f is equal to s squared times the Laplace transform of f. Now we can treat this as an equation for which we're just going to solve for the Laplace transform of f. I'm going to add omega squared times the Laplace transform of f to both sides. So 2 omega s over s squared plus omega squared is equal to, now I'm going to factor out, on the right side, I'm going to factor out the Laplace transform of f. And then that's going to be multiplied by s squared plus omega squared. And if I divide both sides by s squared plus omega squared, we find that the Laplace transform of f is 2 omega s over s squared plus omega squared squared. And there is the transform we were looking for. That's the transform of t times sine omega t. All right, theorem 5 comes as a pair of equations. One that tells us how we find the Laplace transform of the integral of some function in terms of the transform of the function itself. And then the other equation is sort of the inverse relationship if I flip that equation around. So you'll note that we have this new variable. It looks like we're introducing a new variable tau, and you could think of this variable tau as like a dummy variable that we need to throw in. When you integrate this, because we're evaluating it from 0 to t, this will be a function of t as we expect, as when we think about taking the Laplace transform of a function of t that gives us this function of s. And we'll see that work in the next example. So one thing I just want to kind of point out or observe about these formulas in this theorem is that they involve a factor of 1 over s, like taking the transform, big F of s, and then throwing in a factor of 1 over s. You might, if we look back at the last page, the derivative involved a factor of s being added in, right? So take the transform and multiply it by some factor of s. And with the integral, we're taking the transform, big F of s, and multiplying it by 1 over s. So in example 410, we're going to see, we're actually going to use the second equation here. Like, we've been given what the transform is of some function, and we want to find the function of t. So when we do this, we want to observe, first of all, that this is, I'm going to kind of segregate out this factor of 1 over s. This is 1 over s times 1 over s squared plus omega squared. So I want to kind of segregate that out to say, okay, there's that factor. And so this 1 over s squared plus omega squared here, that is the transform of some function. So I want to be able to recognize this as the transform of some function, and if we go back to the last section, it looks an awful lot like this formula here for sine omega t. The difference is that we have 1 on top instead of omega. So 1 over s squared plus omega squared. We could see this as a factor of 1 over omega times omega over s squared plus omega squared. So this function, 1 over s squared plus omega squared, is the transform of, this function here. Or is the transform of 1 over omega times sine omega t. It just has that factor of 1 over omega in front. So now, using that second equation, I've got the inverse transform of 1 over s times 1 over s squared plus omega squared is the inverse transform of 1 over s times 1 over omega times omega over s squared plus omega squared. Now this equation tells us that when I take the inverse transform, this is going to be equal to the integral from 0 to t of, the function that has this as its transform is 1 over omega times sine omega t. And it's sine of omega tau. D tau. So we're going to integrate this. Now 1 over omega is just a constant, so I could pull that out if I want. And when we integrate the sine function, we get negative cosine, and then we need another factor of 1 over omega to compensate for the factor of omega t inside. If we were to take the derivative, right, we'd have to multiply by omega. So this will give us a negative 1 over omega squared cosine of omega tau, and we're evaluating this from 0 to t. So we will end up with a function of t. Alright, so if we plug in our limits, we get a negative 1 over omega squared cosine omega t minus, and it's going to be minus negative, so plus 1 over omega squared cosine of 0. Cosine of 0 is 1, so we get negative 1 over omega squared cosine omega t plus 1 over omega squared. We could leave it that way, or I think what I like to do is just factor out. I'm going to factor out in 1 over omega squared, and inside 1 minus cosine omega t. So there's our function f of t. All right, knowing the, being able to find the Laplace transform of the derivative of a function in terms of the transform of the original function affords us another way to solve a differential equation by really almost purely algebraic means. It transforms it from like a differential equations problem pretty much to an algebra problem, and we're pretty good at algebra, so that's good news for us. The way it works is we start with a differential equation like we might normally solve by some other means, and then we just take the Laplace transform of each side of the equation. And remember that the Laplace transform is linear, so that means we could just apply the transform to each term in the equation and pull out constant factors if we need to. And that gives us another equation which we call the subsidiary equation. And it's an equation where we're solving for the transform, so like big X of S or big F of S, whatever we were calling it. And once we know what that function is, then we just apply the inverse transform to get the function that we're after. I'm calling it big X of S because I'm adhering to the convention that whatever our little function, whatever letter we're using for our f of t, so we're calling this x of t, we just use the capital letter for the transform to get the function of S. So here's an example. X prime plus 2x equals e to the negative 3t. We do have other means to solve this. It is a linear differential equation. We could find, the characteristic equation and, homogeneous and use the forcing function and those other means. But in this case, let's just take the transform of each side. So the transform of x prime, let's go back to this formula at the beginning. We're going to use this formula right here. So the transform of x prime is s times the transform of x minus x of 0. So the way I'm going to write that out, the transform of x prime is s times the transform of x, so that's our big X of s function, minus x of 0, which is minus 1, and then plus 2 times the transform of x of t is big X of s, equals. On the other side, I just need to be able to take the transform of e to the minus 3t. We have that in our table. It's 1 over s plus 3. So this is an equation that we can solve for x of s. So I'm just going to gather my big X terms on one side. And at this point, I guess I'll just point out, I've been using the big X of s notation, like function notation, but it's pretty common for people to just write the big X and leave off like that, the of s part of the notation, just to make it kind of cleaner to solve. And I think I'll do that as well. So I want to solve for big X. I guess I'm just going to add 1 to both sides. And then once I do that, I've got sx plus 2x equals 1 over s plus 3 plus 1. On the left side, I could factor out the big X. On the right side, this is 1 over 1. I'm going to get a common denominator. So we have s plus 3 on the bottom, and then 1 plus s plus 3, or s plus 4 on top. I can solve for big X and say that this is, just by dividing by s plus 2, so this is s plus 4 divided by s plus 3 times s plus 2. So here I have a solution. I mean, this is our x of s function. But it's not quite in a useful form yet, because I want to be able to find little x of t. So I need to be able to find the inverse transform. We're not quite there yet, but we can get there if we find the partial fraction decomposition. So I'm going to set this up as some constant a over s plus 3 plus some constant b over s plus 2. Multiply both sides by the LCD, and we get that s plus 4 is equal to a times s plus 2 plus b times s plus 3. And do a little bit of this on the side. If s is equal to negative 2, then let's see, the left-hand side becomes positive 2, and on the right-hand side, the a term zeroes out, and we get b times 1. So b is equal to 2. And if s is equal to negative 3, then on the left-hand side we get 1. On the right-hand side, the b term zeroes out, and we get negative a. And so a is equal to negative 1. And so now what we have is our big x function, x of s, is equal to negative 1 over s plus 3 plus 2 over s plus 2. And we want the inverse transform of this function, which we can do term-wise. And so x of t, if I take the inverse transform, on the left side I'm going to get x of t. On the right side, I'm going to pull out these constants. So negative 1 times the inverse transform of 1 over s plus 3 plus 2 times the inverse transform of 1 over s plus 2. So we get negative e to the minus 3t plus 2e to the minus 2t. And there's our solution. So this is the total solution. In fact, if we had gone through and found the homogeneous solution and then set up our particular solution to find those unknowns and then put them together, right, but using the means we have already learned, this is what we would get. Notice that when we use the Laplace transform to solve an equation, it kind of bakes in the use of this initial condition. Like, we do this first, right? This goes right in to the function, so it isn't something that I have to do later on to find some unknown constants. I get the total solution at the end in one phase of this problem. So, when we use the Laplace transform to solve a differential equation, it moves it from what we would call the T space into what we call the S space, so that subsidiary equation. So here was sort of the setup that we started with in the last example. We had our given problem, which was the equation and an initial condition. If it were a second degree equation, we'd have x of 0 and x prime of 0. And then we take the Laplace transform, we move it into the S space, and we find the subsidiary equation. So this is sort of after we had taken the transform and we started kind of solving, right, for x of s. We did a little bit of algebra. Then we solved that subsidiary equation. And we solved it in a way so that we were able to kind of split it up. In this case, we used partial fractions, right, so that we were write it in pieces for which we were able to find the inverse transform of each of these pieces. And then we go back to the T space to get the solution to the given problem. All right, let's do another one. In this case, we're looking at a second degree equation. In fact, it only involves a second derivative. There's no first derivative. So the Laplace transform, the formula that we just need here is that the transform of f double prime, or I guess I'll write it in terms of x double prime, is s squared times the Laplace transform of x minus s times x of 0 minus x prime of 0. And of course the Laplace transform of x here is what we're just calling big X. So let's apply the Laplace transform. So we're going to start with x double prime. So that's going to be s squared times big X minus s times x of 0, which is 1, minus x prime of 0, which is also 1. And then when we're going to subtract, and the Laplace transform of x is just big X again. And then on the other side, the Laplace transform of t is 1 over s squared. So we've applied the transform. We want to be able to get an equation, or we have an equation, right, that we can solve for x. So I'm going to throw everything else on the other side. And I'm going to do that by, I guess, adding s and adding 1. So we have s squared times x minus x equals 1 over s squared plus s plus 1. There's a couple things I'm going to do. First of all, I'm going to view this as s plus 1 over 1. And then on the other side of the equation, I'm going to factor out the big X. So we have x times s squared minus 1. On the other side, I'm going to, let's see, I'm going to solve for big X here by dividing both sides by s squared minus 1. So if I distribute this 1 over s squared minus 1 through these parentheses, the first term is 1 over s squared times s squared minus 1. Plus, now on the other term, I'm actually going to get to cancel because remember s squared minus 1, that's a difference of squares. So the s minus 1, or sorry, the s plus 1s will cancel, and I have 1 over s minus 1 here. So this is our x of s function. And I want to get it to a point where on the right side I can take the inverse transform. Now, we can take the inverse transform of 1 over s minus 1 just fine. It's this first fraction that we need to deal with. And we could do that with partial fractions again. I am going to go through that process to show you what we get, but just to kind of be able to go through this and sort of see how the solving by means of a Laplace transform works. I'm just going to tell you how this shakes out when you use partial fractions. And then we'll go from there, and at the end I'll kind of show that process. So when you use partial fractions, that first fraction here becomes, actually I don't need quite a big a fraction bar, becomes negative 1 over s squared plus 1 over s squared minus 1, and then this just gets dragged down here, 1 over s minus 1. So partial fractions gets you this decomposition. Now you might notice that I didn't factor the s squared minus 1. I mean, I could have done this by taking the second fraction, the 1 over s squared minus 1, and breaking that up as an s minus 1 and an s plus 1 and getting two other fractions there. I don't have to do that though, because remember, I'm trying to get this to a point where I can just find the inverse transform. And 1 over s squared minus 1 is in our table. So if we go to our table, we're going to get our x of t function. Negative 1 over s squared, well, that's negative 1 over s squared. The inverse transform of that is t. And then 1 over s squared minus 1, if I have a difference of squares, that right here is the hyperbolic sign. So we have s squared minus 1, so we do have 1 over s squared minus 1 squared. So we don't need to even rewrite it at all. That's just hyperbolic sign when I take the inverse transform, hyperbolic sign of t. And then 1 over s minus 1, that has a inverse transform of e to the t. Okay, let's do another one. This differential equation involves both the first and second derivatives of x. So we're going to need both of those formulas. So let's see, the Laplace transform of f prime, or I guess x prime, is s times the Laplace of x, which is big X, minus x of 0. And then the Laplace transform of x double prime is s squared times big X minus s times x of 0, and then minus x prime of 0. So let's apply the Laplace transform. So first, x double prime, I've got that. This is s squared times big X minus s times x of 0, which is 1, and then minus a negative 3, so plus 3. So this is the first one. Now we have 2x prime as our next term, so I'm going to have 2 times, and then the Laplace transform of x prime. So up here, that's s times big X minus x of 0, which is 1. Notice that I'm multiplying the whole thing by 2, right? I'm using brackets, or you could use parentheses, but I'm going to have to distribute that 2. And then 2x, well, that transform is just 2 times big X. And on the other side, we have 0. The Laplace transform of 0 is 0. Okay, so next I'm going to just clean this up a bit and distribute that 2. So we have s squared x minus s plus 3 plus 2sx minus 2 plus 2x equals 0. I want to solve for big X, so I'm going to, just use our regular algebraic means. I'm going to keep all my x's on one side, throw everything else on the other side. So I've got to get rid of the minus s, the plus 3, and the minus 2. So on the left side we have s squared x plus 2sx plus 2x. And And on the other side now I've got a positive s. Let's see, minus 3 plus 2 is minus 1, so s minus 1. Factor out the big X. S squared plus 2s plus 2 equal to s minus 1. So now we could solve for big X. We're just going to divide by that quadratic. So x, or x of s if you like, is s minus 1 over s squared plus 2s plus 2. So, you know, here's one phase of the problem, right? We take the transform, we use algebra, and we solve for our big X function. But our goal, as always now, right, we want to find x of t, so we need to get this x of s into a form where we now can recognize how to find the inverse transform. Notice that the denominator doesn't factor, so partial fractions isn't going to be much help here, but the other thing that we can always do is complete the square, so let's do that. Now here we're completing the square not to solve the quadratic, but to rewrite the quadratic, and so there is a slight change in our algebraic technique here. So I've got the s squared plus 2s, and now what I'm going to do is kind of segregate out. We got this plus 2, I'm going to write it kind of toward the end. And I know to complete the square, I'm going to add the square of half that coefficient on s. So I'm going to add 1 squared. But I don't have two sides of an equation that I'm working with right now. I just have this one expression. So I'm not adding the same thing to both sides. Rather, I'm adding something and then subtracting that same thing in order to keep this equal to its original form. So now this is s plus 1 squared plus 1. So we have s minus 1 over s plus 1 squared plus 1. So now this is getting closer, right? I have a sum of squares in the bottom, right? The 1 here is the same as a 1 squared. But notice in parentheses I have s plus 1. This is a shift. This is an s shift. And so what that means is I want to kind of break up this fraction by the subtraction on top. And in fact, I want to be able to see an s plus 1 up there, right? So I'm going to go back to this table again real quick. It's that I want to see, like whatever this shift is, I want to see that same expression up top if it's a cosine. Now, when it's a sine, it's just the constant is the same. There's no change up top. We just see the shift in the bottom. But wherever that shift happens, it has to happen everywhere that s appears. So if we go back to this, we're going to do a little algebra. We're going to find a useful way to unsimplify this expression, I guess, so that it reveals its form. This s minus 1, I'm going to write as s plus 1 minus 2. That's certainly equal, right? I mean, if you simplify that, you get s minus 1. And now I'm going to split it up over this subtraction right there. So I got s plus 1 over s plus 1 squared plus 1 squared minus, and I'm going to pull that 2 out. So I've got 2 times 1 over s plus 1 squared plus 1 squared. Now both of these are in the form of something that I can take the inverse transform of. And it has a shift. There's an s shift of -1. So that means this is going to be like this first one right here. This is going to be the transform of cosine of t with the shift of -1, which means it's going to have a factor of e to the negative t in front of it. So this is big X of s, and so little x of t is e to the minus t cosine of 1t. And then minus 2 times, again, this also has a shift because of that s plus 1. So 2 times e to the negative t sine of t. And there's our solution. All right, we're going to end this section with an applied problem. So here's a spring mass system. The spring constant K is 6 newtons per meter. The damping constant B is 5 kilograms per second. We have a 1 kilogram mass, so we know that M is equal to 1. So we start with, of course, our equation is mx double prime plus bx prime plus kx equals f of t, the forcing function. So for us, that's x double prime plus 5x prime plus 6x equals, and then this is 4 times sine of t. Now they tell us that it's lifted up 1 meter, so that means its initial position is +1. And it's given a downward velocity of 8 meters per second, so its initial velocity is -8. And we're going to solve this, and we're going to do so by first taking the Laplace transform all the way through. So x double prime, take the Laplace transform of the x double prime, we get s squared times big X minus s times the initial position, which is 1, minus the initial velocity, which is minus a -8. So there's the x prime. Now the next term, I'm going to have 5 times the transform of x prime. So that's s times big X minus the initial position, -1. And then the last term, 6x, that's 6 times big X. And then on the other side, the transform of 4 sine t is 4 times 1 over s squared plus 1 squared, or s squared plus 1. So we're going to use algebra now to solve for x. I'm going to clean this up a little bit and distribute that 5. So s squared x minus s plus 8 plus 5s times x minus 5 plus 6x equals 4 over s squared plus 1. Gonna get everything without an s on the right side, or everything without an x on the right side, so I'm going to add s. I'm going to subtract 8, and I'm going to add 5 to both sides. On the left side, we have s squared big X plus 5s big X plus 6x equals, on the other side, we have 4 over s squared plus 1, and then plus s. Let's see, I'm subtracting 8 and adding 5, so minus 3 on this side. Going to factor out an x on the left side. And then I'm going to divide by s squared plus 5s plus 6 on both sides. Now note that s squared plus 5s plus 6 will factor. So I'm going to be multiplying by 1 over, and if you factor that, it's s plus 2, s plus 3. So we have x of s equals, distributing that 1 over s plus 2, s plus 3 on the right side, we get 4 over, then we have s squared plus 1, s plus 2, s plus 3, plus s minus 3 over s plus 2, s plus 3. Okay, so our denominators are factored, right? So we've done this first phase where we've got x of s, and we know that what we want is to get it in a form where we can find the inverse transform. These denominators are already factored, and so this should be suggesting pretty strongly that we find a partial fraction decomposition. I'm going to show that process of the partial fraction decomposition at the end. It's a little bit labor intensive, although fun, but right now I'm just going to tell you what we get when we find that partial fraction decomposition, and then we'll go from there. So finding the partial fraction decomposition for this first fraction gives us -2/5 s plus 2/5 over s squared plus 1 plus 4/5 over s plus 2 plus negative 2/5 over s plus 3. So that is this part here. And then the second fraction, this is plus, let's see, negative 5 over s plus 2 plus 6 over s plus 3. So we found the partial fraction decomposition for each, and now I'm just going to kind of do a little bit more algebra to rewrite it to make the inverse transforms easier to find. So this first fraction, starting with the very first one, I've got a negative 2/5. In fact, I'm going to give myself some space here. Negative 2/5 times s over s squared plus 1 plus 2/5 times 1 over s squared plus 1. That is this part here. And then we have plus 4/5. Let's see. Oh, we have some like fractions here, so I'm going to just focus on. I've got this and this, right? Those are both common denominator. So I've got 4/5 minus 5 times 1 over s plus 2. And then I have another pair of common denominators here, the s plus 3. So there's negative 2/5 plus 6. Okay, going to clean this up a little bit. The first terms I'm going to keep as is because those are looking the way I'd like them to look. Four-fifths minus 5 is negative 21 over 5. And then negative 2/5 plus 6 is 28 over 5. Now, so here's our x of s. Now we're ready to go find the inverse transform of each to get x of t. This first one, again, if you take a look at the table, you'll see that this is the transform of cosine t. So I have a negative 2/5 cosine t. And then this next one, positive 1 over s squared plus 1, that's the transform of sine t. So I have a positive 2/5 sine of t. And then these last two are transforms of the exponential function. So I have minus 21 over 5 e to the negative 2t and plus 28 over 5 e to the negative 3t. And there's our solution.